Hi guys, my name is Nikolay Grishchenko and I've been writing in Python since 2014. Mainly web applications and some data processing, but what's more important is that I have been working with cloud providers for almost twice as long. I'll skip the agenda part to save some time, and actually I try to do this almost always now. What is the most common thing that you do first thing when you meet some new technology? You open Wikipedia, right? So I don't know, maybe the problem is that English is not my first language, but if I haven't been working with FAST for many years, this text would still confuse me. It's boring. But we shall go a little under the hood and make everything clear. And just before that, let's make a short notice about the current big players in the FAST market. Amazon Web Services, Microsoft Azure, and Google Cloud Platform, they all provide this or that kind of function as a service, and they all support Python. I shall use some examples and some terminology even from AWS environment, because they are definitely the most advanced player with regards to serverless. But please keep in mind that all these provide infrastructure for function as a service. As I promised, we shall go under the hood soon, but let's take a look at the exterior first. I have showed here the user as a human side, but in the reality, the user of a function is not really a human. In most cases, this is some integrated service or another function that invokes your function. And actually, programming functions is almost all about event-driven programming. Events come to the cloud provider API, some magic happens behind the scenes, your code gets executed, and the result may be returned to the user. Actually, this information is usually enough to start programming functions and to understand already some of their value. We want to know some more tricks. Here comes a very simplified schema of what's going on. When your event comes to the API, it first gets to the router. The router then asks the worker manager for a free container with the required code already installed. The worker manager then spawns a new container and returns its location back to the router. The router passes the event to the container, your code gets executed, and it then returns back to the API and to the user. In this schema, I call this a worker, and it may have different terminologies in different cloud environments. In AWS, it's called a sandbox. The idea is more or less the same. This is one of many containers with your code that will actually process the event. Looks a little bit complicated, right? Especially launching a new container for every request. And the good news is that this actually happens very fast, especially in dynamically interpreted languages like Python. But still, there is a faster way. In case there are free workers from previous executions, the worker manager knows this already. He can simply tell the router to send a request there and save all the time for spawning a new container. This is called a warm execution. It means that you already have an idle container waiting for requests. The sad part is that this logic of worker manager is completely hidden from you. Sometimes it can terminate containers very soon, like seconds or minutes after they become idle. But in many other cases, it may keep warm containers for a long time, actually up to 24 hours, which is maximum lifetime. Your code, as I have mentioned, is deployed and executed on the worker container. And you have to write this code in order to optimize for both cold and warm starts. Here comes a very simple code that emulates some work that could be done only once during the lifetime of the processor class. Let's say it's building some cache, fetching some external data. In this example, we simply sleep to emulate this work. The important thing to remember is that the main model is read by the Python interpreter only once during loading of the container, during the spawning of the container. And when the event is coming from the router, it just calls the handler method. And your event, as you can see here, comes into that handler function. So I have marked here in red lines of this model, the code that will be executed during the cold start. And in green, the code that will be executed during each call, both cold and warm. As you probably see, we have a problem here. This heavy work of initialization will take every time because we reinitialize the processor for every call of the handler. But really, we don't have to. Look, just moving the initialization of the processor outside the scope of the handler function will dramatically improve the performance of all warm executions. Now, the red part is what happens before the request from the router even reaches your code. The green part is executed almost instantly in this example. I specifically showed this example with code because this is a very common mistake that makes some developers feel skeptic about FAS, and when they check their response time statistics and the bill.
Okay, here comes a list of topics for you to keep in mind always when writing FAS code and when architecting FAS-based microservices. The first thing we already discussed: keep heavy things away from the handler of your function. Now, the package size. When a new container is spawned, it downloads the package, your code, by network to the container. It does not spawn a container from your image. This happens very fast, but you should still always try to minimize the size of your package. If you really need some heavy external libraries, use layers. This is another way to mount some read-only disk already with your code to the container. This happens extremely fast, but this makes managing the code more complicated. Isolate the zone of responsibility of your microservices. Do not implement too much steps in one function. Next, computed memory is very cheap. As we remember, once initialized something outside the scope of the handler, this stays in the memory for future invocations. Use this for all kinds of caching. And frameworks. There are frameworks now that help you create web applications, serverless, that will handle CI/CD for you. There are great frameworks to optimize logging, tracing, metric collection, simplify and optimize almost everything. Just check the list of links in the extra materials for this talk. Reserved concurrency. There is not that much to add to the title, and you probably remember that the worker manager always knows if he has any idle containers, and frankly speaking, he can even predict if after a few milliseconds he will get a one. But what we really want is, in this case, for reserved concurrency, is to always have a sufficient number of warm containers. This is doable, at least in AWS, for about 2 years. You just pay some reservation fee, and you have the required number of always warm containers. But this actually moves us a little bit away from the serverless methodology, from the serverless way of thinking towards the regular containers. Still, this option is useful, especially for transition periods when migrating to the cloud, when you did not yet re-architect your applications following serverless best practices, but you want to use the technology for some other benefits. What are the common scenarios for function as a service? Well, these scenarios are usually dictated by the limitations that this technology has. Let's take a look at these limitations. First of all, we're living in a very dynamic era. The limitations are changing every quarter, every month, every week, and we'll just take a look at what we can control now, but we'll not use any numbers here. CPU, memory, and network. They usually scale linearly, And for simple workflows, you may consider that the more resources you provide to the container, the faster, in most cases, your function will execute. This is not proportionally, of course, but still there is a thin line when you want to find for each specific function the optimal resources that you want to provide for this function to optimize for cost or for performance. And there are plenty of benchmarks and tools for that. The second limit is the maximum execution time. It's frankly speaking, a much bigger challenge when you design your software. And I will now show some very common scenarios where serverless functions work great, and some where it might need some tricks. First of all, HTTP APIs. This is actually a slide from my talk in PyCon 2019. And maybe some of you remember it. No surprise, this one is a little bit outdated. What was happening here in this one, when the HTTP request was coming to the API gateway, then translated to the function, then the function did some operations with the database. There are still some use cases for this, especially if you need some heavy logic on top of the data. But for regular CRUD operations, there is a direct integration. There are actually plenty of direct integrations right now, and you can actually skip the function and integrate your API with the data source database directly. And as you all know, the best code is the one that you don't have to write. Another scenario is stream processing. For heavy load event-driven workflows, you can integrate serverless functions with your data pipeline and process events from the pipeline. The function may take the data, transform the data the way you need, forward it somewhere, let it be to another stream and some queue, or save it in a permanent storage like a database. In this case, you usually care less about scaling, but more about the simplicity of development and easiness of debugging. You can save a lot of development time if you chunk your data workflow processing to microservices, and each one will do its own job. And now comes the fun part. Web scenarios that I displayed earlier are synchronous. This means that the one who calls the function waits for the response. Whatever the function will return will go to the caller. But this is not the only way to use serverless. Not all functions actually have a return value. They simply can accomplish some work and return none. So why should a caller wait for this none? The real effectiveness here comes with asynchronous calls. This is the way when you invoke a function, send some input payload, and you don't wait for it. The function accomplishes its job, probably reports something somewhere, for example, send some artifacts to the storage, or save something to the database, or maybe send a message to the queue in order to continue the workflow. But this becomes the responsibility of the function itself to make sure that the workflow will go on. And this is actually bad. This could be a problem. This is where the orchestration is required. And we'll talk about different ways to orchestrate serverless functions in a moment. What should the orchestration mechanism care about in the context of FaaS? Failures. Functions fail, everything fails. Because of some invalid input data, of some casual unhandled exception, we will retry it, and for this to happen smoothly, the function payload must be isolated, independent, and safe against duplicate calls. If a function works with anything external, API, database, storage, these ones will throttle. Throttling on its own is an example of a well-architected API. Stable services should not try to process enormous spikes of requests. Throttling is a natural way of services to tell one another that you should slow down, relax, drink some coffee. So your invocation of new functions should respect throttling of external services and use exponential backoff. And now we come to concurrency. You can set a custom hard limit of concurrent executions per function, but what the orchestrator mechanism should care about is the environment. And by environment here, I mean external services used by specific types of workers. Should always monitor the average duration of your workers. And if it's increased, probably something is throttling. Probably you should have less concurrent executions. Unfortunately, there are no out-of-the-box services to solve all of these problems. But still, there is a recommended pattern for this, and it's called state machine. State machine is some virtual machine that is guaranteed to run permanently during a single run of the whole workflow of serverless scenario. And let's describe this pattern with an example. For example, you upload an image to a storage, and then have to call 3 different workers to resize the image to standard definitions, to create a thumbnail, to optimize the compression of the image, and to construct a cloud of tags using some image recognition tool, for example. Then you report this image as processed, for example, to some database, and after that appears as available in your CMS. It doesn't matter here if you upload 10 images per day or 10 images per second. Your workflows are absolutely identical. You may want to configure different steps of these workflows as serial or parallel. You may want to pass artifacts and parameters between these stages. You definitely want to retry some failed steps. For example, if optimizing failed once, you can retry it and the next time it will run. And this is what the state machine takes care of. It orchestrates transitions between steps of the workflow. But all the same, you have to orchestrate only the workflow within a single image. And here is another scenario, a little bit less common for serverless functions. This is when parts of your workflow are big. Each step then takes multiple invocations of the same function to process chunks of the payload. And here, the environment status is even more important. Imagine that the first step of yours is to pull and ingest some batch of reports from an external API. Let's say it's not that big and you can intuitively chunk it to 1,000 function executions. If you run 1,000 invocations in parallel, you will kill the API. If it's smart, it will throttle you as described above, or it will simply die and consume your money along the way. If you run these invocations one by one, then you will never see the end of this process. It will simply take too long. And what you really want to do here is to dynamically orchestrate the number of concurrent runs for a specific function. You can, of course, write this logic and run it on your own state machine. Probably even take some parts of this in step functions or their analogs, but we are talking serverless here. In my company, we made a complex of microservices for orchestration of other microservices, and we called it Soso, for serverless orchestration of serverless workers. The system is used for more than 2 years in my company, and today it supports about 150 different types of Lambda workers with millions of asynchronous daily invocations. And the good news is that the project is open source, it has a growing number of external contributors, and I shall now spend another couple of minutes to briefly describe the main architecture here. Now, let's have a look at several essential components required for orchestration. From the name of the package, you probably already guessed that they are serverless functions themselves. First one comes the scheduler. Its main goal is to transform some incoming business job to one or many tasks for workers. There is a built-in chunking mechanism that extracts parts of the big JSON and chunks it to smaller payloads. Each task here represents exactly the payload that a single invocation, a single run of the worker will receive. Remember that event in the example. Now, the question is how to chunk. All these rules come in the config of the scheduler, so you can configure differently for different chunking mechanisms for different functions. And these rules may be both built-in mechanisms or your own custom method that you implement in your scheduler. The chunking mechanism goes into the JSON recursively if required. And the last stage is sending this task to the stateful queue. So why stateful? Because tasks should remain in the queue during the whole life cycle, since the scheduler first creates it, and then the task until the task is completely solved and verified. We used DynamoDB for this, and with correct indexes and known set of queries, it gives super fast performance. So it's super easy to implement. The documentation of Soso has a sample CloudFormation template and instructions how to set up the whole environment within several minutes. And the second essential function of Soso is the orchestrator. The orchestrator runs automatically every minute. And during this run, for each of the configured types of workers, he mainly answers a single question. How many new workers should I invoke at this current moment? This sounds easy, but you have to respect a lot of things here. First of all, we can configure a hard limit of concurrent invocations. The orchestrator will first evaluate the status of previously invoked tasks and their duration. And next, we have to respect the environment the worker may depend on. These can be databases, virtual machines, storages, API, whatever your specific worker integrates with. And AWS has a great tool to aggregate custom metrics. In fact, most of these metrics are already aggregated by most of the services automatically by default. And this is CloudWatch. So you can provide configuration for CloudWatch metrics to be evaluated for a specific worker, and then the orchestrator should respect these metrics. And more than half of the presentations, usually during conferences, end up with we are hiring. So we are not, we are an open source project and we are looking for free contributors. I really hope that my talk has inspired those of you who did not yet use FAS to give it a try, maybe with your next mini project or your next mini task. And those of you who already use serverless, great, let's collaborate. Let's share the knowledge, let's spread the knowledge, and thank you all for your time.